Hello, chemistry. Good morning. Uh, Happy Tuesday. Happy birthday, Tuesday, if you're here today. Sorry I'm not in today. Still not feeling well. Gonna take another day and try to recoup. Hopefully I'm back Wednesday. But we need to get through some stuff so I don't send you guys off to break with homework. So let's get down to it. Today's lesson is starring Mr. Greer. Surprise, it's me. Still kicking. All right, so when we left off, we had talked about the difference between ionic, covalent, and polar covalent bonds, and we had talked about those electronegativities, and you guys used the periodic table to find those that kind of chart with those numbers on it. So normally, when we have chemical bonding occurring, it's a energy releasing process. So normally, like when we burn things, there's chemical bonding happening there between the carbon in the wood and the oxygen in the air, and this releases energy in the form of heat. So to break bonds, like if we're going to boil water and we're going to break the bonds between those hydrogen and oxygen atoms, we need to absorb energy. We need to add energy in. So by bonding, what happens is all of these atoms that are in the universe that are all free floating, it decreases the potential energy of that combined atom, that combined unit. I'm going to go through these notes pretty quickly, just for the flow of it. You guys can pause at any time and make sure that you guys have all the information. You'll see some flashes. William's watching some Netflix, so we're kind of having a busy time here. All right, so a molecule, the definition of a molecule is the smallest unit quantity of matter which can exist by itself and retain all the properties of the original substance. So this could be like helium. It could be like water is a molecule. One molecule of water is H2O. H2O. It can be diatomic, meaning it has a molecule containing two atoms. This is actually how we make water. We take hydrogen, H2, and we add oxygen gas, O2, and this will go to H2O. We're going to talk next chapter a lot about how this is kind of misleading because this is actually two H2Os being made here and two molecules of this being bonded. So it's actually two hydrogen gases plus two oxygen gases, four, excuse me. All right. So molecular compound. This is a chemical compound whose simplest formula units are molecules. So this would be something like water. A chemical formula, represents the relative number of atoms of each kind in an element by using their atomic abbreviations and subscripts. So in hydrogen gas, it is 2, the subscript 2 means there are two molecules of this H, this hydrogen. And the same thing with this little more complex molecule, glucose. There's always 6 carbons in glucose, 12 hydrogens, and 6 oxygens. And a molecular formula shows the types and numbers of atoms combined in a single molecule. So this would be both the chemical and the molecular formula for glucose. If you had more than one, like in that last example where I had 2 hydrogen atoms, that would be the chemical formula, even though the molecular formula is a little bit simpler. All right, to the formation of covalent bonds. So we've talked about what a covalent bond is and what the electronegativities need to be, but how do we actually form one of these guys? This is tea. I'm not drinking coffee this late. 2 hydrogen atoms at a great distance have no influence on each other. This is the same thing with magnets. If you have 2 magnets that are really far away from each other, they have no affinity towards each other. Each one of them has a proton, and each one of them has an electron if it's a neutrally charged hydrogen. Now, if they were to attract each other, it would decrease their potential energy. So we've talked about they want to have this outer shell. They want to be happy atoms. This would be attracting if they decrease their potential energy. Repulsion would mean it was increase in potential energy. This is what you'll see a lot of, like if we have the noble gases that have a lot of negative electric charges around them. They don't want to be around other negative charges. They want to stay away from electrons. They're repulsed by them because adding one would increase their potential energy. Molecules form to form more stable things. They always go towards more stable. So bonding makes a product with a lower potential energy. Remember, potential energy is the energy that you have to do work. Lower potential energy means less likely to be reactive, less likely to, cause some kind of chemical reaction, less likely to, you know, be unstable. Bond length, not all bonds are the same length. Some are short, some are medium length, and some are long. Bond length is the average distance between two bonded atoms. So in our polar atoms, like oxygen and hydrogen, these bonds are a certain distance apart. And this bond length is the distance of the minimum potential energy. So once again, these are going to form the most stable molecule they can. They're not going to have, one hydrogen super close with its electrons like right up against the oxygen and one super far away. Like, this is not a favorable way to make a molecule. There's a lot of energy here. This hydrogen, these negative and positive charges are going to want to repulse each other, and this one's too far away. It'll just fling off into space and leave this guy charged. The bond energy is the amount of energy it takes to actually break a chemical bond. So if we were to take this nice water molecule and cleave off this hydrogen here, that would take a certain amount of energy. Normally, even boiling water isn't enough energy to release this bond. It just makes these bonds longer so that this can escape into the gaseous form. So the energy reported for bond energy is the amount of energy required to break one of the bonds in its gaseous form. So when we have this water molecule as a gas, to break a hydrogen off is the bond energy that would be required. All right, octet rule. This is all molecules, all atoms want to be stable. So the octet rule, it means that each atom will, by gaining, losing, or sharing electrons, should end up with an octet of electrons in its outer shell. Now, octet, remember when we did Lewis bonding, we talked about hydrogen has 1 in this s orbital, and helium has 2. Remember that they only have that first s1 orbital, so this s1 orbital with these 2 in it, s1, is happy. But in the next row down on the periodic table, row 2, we go all the way out to like neon at the end. Let me grab a little more exciting color. Neon ends up having 8, or an octet, of electrons, with each of these orbitals, the p orbitals and the s orbitals, all filled. This is a happy element. This one's very happy. It's got what it wants. So the noble gases already are in this octet rule. They already have this 8 filled, or in the case of helium, 2 filled. The rest of them either need to gain an electron, lose an electron, or share an electron to look like a noble gas. Their goal is to look like a noble gas, to have all these electrons filled up around them. Now, we talked about Lewis dots earlier this semester. You remember for hydrogen, it looked like this. Now, we also use them to represent molecules. So in a diatomic hydrogen, meaning 2 hydrogens bonded together, it'll look like this, with this blue electron belonging to this blue hydrogen and this black electron belonging to this black hydrogen. And this is H2. This is the molecule H2. These guys are sharing them. So now both of these have this filled s orbital here. So they both look like helium now because they both have those two electrons. Now, to make things a little bit more simple, you have seen like around my room, there's serotonin. There's some couple of other elements that are bonded, they're formed like this, like a bunch of C's and then H's coming off of these. These are all chemical bonds. Each one of these lines is a chemical bond. So if we're going to draw this structure above, HH, you can see it here in this example, we're just drawing it with these lines. Now, remember that one of these, and I know the blue's a little hard to see there. Let me go red, a little bit bolder and brighter. So remember that this is still 2 electrons. One line, one solid line is 2 electrons being shared. And that's going to be important coming up because we're going to have more than one line. So if we have an unshared pair of electrons, like let's say for example, they're not involved in bonding, they're just floating around. Remember how in Lewis dot structures we would draw, like Cl had 1, 2, 3, 4, 5, 6. I'm sorry, those are really small. And 7. I don't think I can make them bigger. We have 7. We'd have this one extra one floating free. So Cl actually ends up having, and this one's, you can see 2 of these here, but that's not the octet. So it needs to actually look like this. Write this one down instead. So it has that bonded one here, so that's 2 electrons right there. And then it's going to have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm getting that 1, 2 from this line here because that's 2 electrons there. So this is what the Lewis structure of chlorine looks like when it's there. We don't show all lone pairs. Don't get lazy like Mr. Greer did up here. Don't be like Mr. Greer. You guys are better than that. It shows all the lone pairs in the outer layer. So if it show all 3 of these pairs, 1, 2, 1, 2, 1, 2, in the outer layer, 6 total electrons. All right, structural formula. This indicates the kind, the number, the arrangement, and bonds of atoms in a molecule. It does not designate the lone pairs. So in ClCl here, this first example, you don't see those lone pairs. When we draw them out, we show them, but when we just write them, we don't. Another example is this H2O of water. This does not show lone pairs. If we were to draw it, it would be 2 shared there, 2 shared there. Oxygen normally has 6 valence electrons, so it's picking up 2 extra ones from here and here. So it will have 1, 2, 3, 4, 5, 6, 7, 8. Excuse me. 5, 6, 7, 8 for a total of 8, and it'll be happy. It'll be an octet. So in a single bond, we have 2 electrons being shared, 1 from each atom. In a double bond, like in diatomic oxygen, oxygen has 6 valence electrons, and it needs to get up to 8. That means it needs to share 2. So it'll go 1, 2, 1, 2. Each one of these is sharing 2. So right here, there's 2 electrons in this line and 2 electrons in this line for 4 electrons. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And remember that you're looking at the periodic table, you're seeing what group these guys are in, and then you're doing those s and p orbitals, and you're remembering that, how much they have in there. Remember, you don't show anything from the line before, so for oxygen, you don't show those 2 that are around that helium molecule. You forget these 2 in that full shell of the helium molecule before you go up to oxygen. All right, multiple bonds. You can have triple bonds where it's like nitrogen will be 1, 2, 3, nitrogen, and then it'll have a lone pair. Here and here, here and here. 2, 4, 6, 7, 8. So you're always trying to fill the octet rule. And on today's assignment, you might have to get a little creative to get there, because some of them are a little trickier. All right, polyatomic. These are, they form ions rather than neutral molecules. There'll be a charged group of covalently bound atoms. They do not exist like normally. They're found in chemical compounds with ions of opposite charge. For example, like NaOH3 will sometimes be found as HNO3, and this H will be an extra proton, so it'll be a positive, it'll be just a neutrally one. But the nitrate ion is NO3 minus, and then this is the ammonia ion, ammonia, NH4 plus. So polyatomic ions, it's in the name, they are going to be an ion. They're going to have some charge, whether it's positive or negative. They can be anions or cations, or as Bella calls them, catonions. Resonance, this is kind of an advanced concept. This is the first time you guys are going to see this. This is bonding of elements that can't be represented by a single Lewis structure. So all 3 of these, 1, 2, and 3 here, are the exact same molecule. They're not exactly the same, but they are different possible configurations, and each one of these is likely to occur. So you can either have the negatives on these two oxygens, you can have the negatives on these two oxygens, or the negative on this oxygen. And you can see that this double bond is changing positions too. It's going to find the one that is the least energy, the one that has the lowest amount of energy for whatever situation it is, whatever molecule it's bonded to, or whatever substrate it's in, whatever fluid it's in, whether it's a basic or an acidic fluid, it's going to change its identity so that it matches that. So that's what resonance boils down to. I don't think you have any resonance today on your assignment, but that's what resonance is all about. All right, I wanted to give you a couple practice problems. Your guys' job today is going to be taking molecules and making them into Lewis structures. So you're going to have you're going to have single bonds. Sorry, apologize. Your very first one is going to be a diatomic H2. Remember that hydrogen normally has one valence electron, and you can draw these out and think, okay, I know one hydrogen has one valence, so to get it to bond, it's going to look like this. And you could draw the dots if you want, or you can draw the line, or both. It's good practice right now to draw both, because the lines are how we're going to get there. You guys are going to be advanced. You guys are going to understand that. All right, our second example is Br2. Well, remember that one Br, one bromine, it's a halogen, exists over in almost the very far right. So it's going to have 7 electrons on the outside. So it wants one more electron to get to a nice happy 8 shells. So it will form one bond, getting an extra electron from another bromine. Sorry for my line, it's a little wonky. Then we'll have 1, 2, 3, 4, 5, 6. So this atom has 1, 2, 3, 4, 5, 6, 7, 8, and then this one will match it. 1, 2, 3, 4, 5, 6. And then for our last example, beryllium Br2. Beryllium Br2. Beryllium is kind of special. It only needs 4 electrons in its outer shell to be happy. It'll say that on your assignment if you see that. So Be normally has 2. It will make it 1 connection with Br on one side and 1 connection with a Br on the other side. Because those Brs once again have 7. So I have 1, 2, 3, 4, 5, 6, 7, 8 in the middle there. 1, 2, 3, 4, 5, 6, 7, and 8. And then beryllium has 2 here and 2 here for a total of 4. So beryllium's happy. All right, I'm going to give you a couple examples of some polyatomic ones, and then we'll be done for today, and I'll let you guys work on your assignment. If you have questions, circle them. You can email me, of course. I'll be on and off of email, just depending on when I'm napping. I'm trying to get back up to full strength to be able to enjoy the end of the week with you guys. Feels weird being sick on before break. Okay, and then the second one is multiple bonds, and we're going to do some multiple bonds. Oops. Sorry, I was trying to keep this video under 20 minutes, but I don't know that I'm going to do it. That's all right. So the first one is silicon oxygen, so SO2. In this one, you're going to have to use some double bonds because everyone wants to have 8 electrons. Oxygen normally has 6. 1, 2, 3, 4, 5, 6. Mr. Greer almost got sloppy. And then silicon has 4. 1, 2, 3, and 4. So in this case, silicon and oxygen need to get up to a total of 8 electrons. So, makes sense. You would probably try to stick silicon in the middle and go, okay, well, I have an oxygen on this side and an oxygen on this side. So I'm going to real quick just use this electron there and this electron there. So now silicon has 1, 2, 3, 4, 5, 6. We're missing 2 on silicon. And oxygen has, because it's only used 1 of these in that bond, 1, 2, 3, 4, 5, 6, 7. Now if you get tricky with it and you put a double bond on silicon here, now we've used up 2 of the oxygen ones and all 4 of the silicon ones for bonding. And silicon now has 1, 2, 3, 4, 5, 6, 7, 8 for silicon. And then the oxygens have 4 here, and then they have the 4 that are left over here. So 1, 2, 3, 4. 1, 2, 3, 4. And everyone in this molecule has 8. And you'll have to get tricky with it. You'll have to try giving and taking and mixing and matching and figuring out which ones go where. I'm going to give you one more example from your assignment real quick, and then I'll let you go. Erase, 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 erase. Missing my Promethean right about now. All right, your next one is going to be COCl2. And one of the beautiful things about carbon, and I'm going to talk about it every chance I get, is carbon makes 4 bonds. It likes to have 4 friends. And if it can't have 4 friends, then it likes to be friends with somebody double. Now, carbon is going to have 4, so it needs another 4. Oxygen has that 6 that you've seen. And chlorine has 7. It's a halogen. I apologize that these are a little sloppier than I normally draw. Maybe a little sloppier. So carbon is going to hang out here. And right off the bat, let's just draw. It's going to bond to a Cl. And it's going to bond to a Cl. Because these Cl's just need 1 electron. So now we've used 2 electrons from carbon. And we've bonded this one here on Cl twice. There's 2 of these. So Cl's now have 1, 2, 3, 4, 5, 6, and then in this bond, 7, 8. And the same thing on this side. Now carbon right now, it has 2 valence electrons left, and it has 1, 2 here and 1, 2 here for a total of 6 electrons. It needs to get up to 8. It needs 2 more from somewhere, and oxygen has 6 and needs 2 more. So they're going to share 2 this time for a double bond to oxygen. This will be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. There'll be 8 bonded there. So now carbon's happy, and then this oxygen will have, we bonded 2 of these. Let me cross them out. 1, 2. It still has these 2 left over, 4 left over, excuse me. 1, 2, 1, 2. So 1, 2, 3, 4, and then 5, 6, 7, 8. So that's a total of 8 for all of these. They're all happy. These ones can get a little tricky. Take your time on them, and we'll work on them on Wednesday if you have any questions. Try to finish them all. If you have questions, circle the ones that you don't quite understand, but try to finish them all, and then we'll correct them. All right. Hope you guys have a wonderful day. Miss you. Ciao, ciao for now.